In September 2022, after 8 years operating in Martian orbit, the Mangalyaan spacecraft slipped into the dark shadow of Mars. It lost direct line of sight with the sun, and its solar panels stopped generating power. Eclipses are a standard operational hazard in planetary orbit, but the geometry of this specific alignment resulted in a prolonged Martian eclipse lasting roughly 7 hours. The probe's onboard battery was designed to handle brief periods of darkness. It carried a maximum rating for only 1 hour and 40 minutes of backup power. As the shadow persisted and the battery drained past its limit, spacecraft experienced a cascading failure. Temperature control systems shut down in the deep cold of space. The communications array went silent, and the battery suffered terminal depletion. Mangalyaan succumbed to an unavoidable celestial alignment that exceeded its designed thermal and electrical tolerances. During its 8-year lifespan, the probe beamed an immense volume of raw data back to Earth. ISRO received 2 terabytes of telemetry and observations from Martian orbit. Over 32 independent research teams spent years analyzing that data. Yet the total scientific output from this massive dataset resulted in only 27 peer-reviewed published papers. To understand that number, we can look at NASA's MAVEN mission, an atmospheric probe that arrived at Mars in the exact same year as Mangalyaan. Using the data collected by MAVEN, international scientific teams have produced over 500 peer-reviewed papers. Mangalyaan was a landmark in cost-constrained engineering, yet its limited scientific output highlights the operational challenges of detecting trace elements and the necessity of a dedicated research infrastructure. The primary logistical hurdle for ISRO was the launch vehicle itself. They relied on the Polar Satellite Launch Vehicle, or PSLV. When NASA targets Mars, they typically utilize heavy-lift rockets capable of executing direct Hohmann transfer orbits, shooting a spacecraft straight out of Earth's gravity and directly toward a Mars intercept. The PSLV lacked the necessary thrust, the total change in velocity, known as delta V, to push the Mangalyaan payload directly out of Earth's gravitational well. ISRO engineers developed a multi-stage perigee-raising maneuver, using Earth's gravity as a slingshot. Every time the spacecraft reached its closest approach to Earth, the engines fired, gradually stretching the farthest point of the orbit deeper into space. The margin for error was razor-thin. If the angle or duration of any perigee burn was slightly miscalculated, the spacecraft would either crash back into Earth's atmosphere or miss the Mars intercept window entirely. On December 1st, following 6 precise orbital expansions, the final trans-Mars injection burn fired, and Mangalyaan successfully broke free of Earth's gravity. Successfully reaching a Mars trajectory under these strict delta-V constraints validated ISRO's ability to execute complex, multi-burn orbital maneuvers. Because of the fuel required for those extensive orbital maneuvers, the spacecraft faced extreme mass restrictions. Comparing the two 2013 missions, ISRO executed Mangalyaan for $74 million, carrying a 15-kilogram payload. NASA's MAVEN cost $671 million, allowing for a 65-kilogram payload. Mangalyaan's tiny 15 kilograms was split across 5 constrained scientific instruments. But capturing data in space is only half the equation. When an instrument beams back complex raw telemetry, like atmospheric moisture readings, that data requires an extensive planetary science ecosystem on the ground to process and interpret it. NASA benefits from a massive network of university researchers ready to parse incoming data. ISRO's planetary science infrastructure, by comparison, was still in infancy. The low publication count stems directly from this bottleneck. Without a vast, well-funded academic workforce dedicated to cleaning and interpreting the 2 terabytes of raw telemetry, much of the data remains unanalyzed. The most anticipated instrument among Mangalyaan's 15-kilogram payload was the methane sensor for Mars. Methane is a critical biosignature. On Earth, the vast majority of methane is produced by living organisms. Finding it on Mars would be a strong indicator of subsurface biological or geological activity. Detecting it is exceptionally difficult. The sensor needed the sensitivity to identify methane at concentrations of a few parts per billion. Furthermore, the Martian atmosphere is composed of 95% carbon dioxide, creating a massive chemical obstacle for the sensors. This chart plots the infrared absorption spectra for atmospheric gases. Here is the massive absorption peak for carbon dioxide. The problem occurs right here. The spectral bands for methane and carbon dioxide overlap at these specific wavelengths. Due to strict weight limits, Mangalyaan's sensor lacked the high resolution required to differentiate between incredibly close wavelengths. It physically could not separate the faint methane signal from the overwhelming noise of the carbon dioxide. Confronted with this physical reality, ISRO scientists repurposed the instrument into an albedo map, using it to measure solar reflectance off the Martian surface instead of hunting for gas. Tracing methane is notoriously complex. Even NASA's Curiosity rover and the European Space Agency's heavily funded Trace Gas Orbiter have struggled with conflicting readings and false positives in the Martian atmosphere. The sensor's failure highlights a fundamental constraint in planetary exploration: the difficulty of maintaining high signal-to-noise ratios in atmospheric measurements on a strictly limited budget. Looking at the dead spacecraft drifting in Martian orbit and the lack of high-profile scientific papers, it raises a simple question: did the mission fail? Evaluating Mangalyaan purely on its scientific output applies the wrong metric entirely. At its core, the Mars orbiter mission was a deep space technology demonstrator, designed first and foremost to prove India's systems engineering and navigation capabilities. The hardware survived a 300-day transit through deep space, successfully managed complex thermal dynamics, and executed an autonomous Mars orbit insertion. Because of the 12-minute signal delay between Earth and Mars, that critical insertion burn had to be entirely automated. The celebration in mission control reflected the successful completion of an entirely autonomous orbital insertion, an engineering milestone that redefined India's capabilities in deep space. The specific orbital and navigation techniques pioneered by Mangalyaan established the technical baseline for ISRO's future interplanetary missions. When ISRO targeted the Moon with Chandrayaan-3, they relied on the exact same multi-burn, perigee-raising orbital mechanics to escape Earth's gravity on a budget. The autonomous navigation software and deep space telemetry networks built for the Mars mission directly informed the systems that successfully landed Chandrayaan-3 on the lunar South Pole. India's planetary science ecosystem is currently expanding to match the capacity of its rockets. The engineering foundation is now fully operational. Mangalyaan sacrificed high-fidelity scientific payloads to achieve a specific goal, proving that a cost-effective space program can master orbital mechanics and successfully navigate the most unforgiving environments in the solar system.